All right, line P3, learning task 2. This is the second video inside of our learning task 2 series here, where we're now going to go and take a look at delta to delta transformer banks. And we do have places that we especially like to go and use delta, particularly in medium voltage ranges and when we're dealing with loads that are going to be balanced three-phase loads that don't need a neutral. So electric heat, three-phase electric heat in industrial processes, or motors in industrial processes, or sometimes even a sub-distribution, just knock it down to a safer level, and then from there, drop it down to one smaller. You might be on a larger system where you have got like a 25,000 volt system, and then you're going to knock it down to 600, carry it around as a 600 delta system, and then at your individual places where you need to bring it lower, you take it down to the 122.8. That might be your utilization, etc. But it's more of a medium voltage range than anything else. The Y was a high voltage one because we could get away with having a high line-to-line value of voltage, but our phases only had to be insulated to the phase value. You could be a 25,000 volt line with only a 14.4 kV phase value that you'd have to go and insulate to. But in our deltas over here, we just deal with, generally speaking, we're able to get larger line currents out with smaller windings, but we just cannot go and have any sort of an unbalanced load with them. As soon as we would unbalance the load, the windings would get differing values of voltage drop, and we would start running into problems with that. Anyways, for connections on these, the three diagrams, 16, 17, and 18, show us starting to go and make those phasor diagrams. I'm going to go through the same steps as what they're doing, but we're going to draw it all out on this blank sheet that we have over here. First thing that we are going to do is we have a delta to delta. We are going to go and split the page down the middle. We're going to go and say that one side is going to go and be my high side. The other side is going to be my low side. I'm going to designate that with an X because that's the standard when we're dealing with transformers. The next thing that I'm going to do is I'm going to start with my conventions. My convention is that I'm going to go and have my phase A, and then from phase A, I have got a 30-degree phasor that's going to come off, and that 30-degree, working as A from our origin, is going to go over to the point that we would go and term as being neutral. Now, I know on a delta transformer, we don't actually have a neutral connection, but the neutral is going to be centralized. It actually exists, and all the other points are going to be balanced around it. The second thing that we have to do is we have to draw a line at 60 degrees. That's going to be this one over here. And that 60-degree line is going to point to where we are going to go and drop our B phase. One second. Let me just erase that there. Where I'm going to go and drop my B phase over here. Then we're able to now start building the rest of our transformer connections. So now that I've got those two, which are my basics laid out, I'm going to erase all of that because those were just reference vectors, and I'm going to start making my actual connections. The connections are always going to go and follow the letter. We know where A and B are, therefore we also know where C is going to go and be. And what I'm going to do then is for each of my transformer phases, I'm always going to start with the number 1 of that transformer that is going to go across. In other words, over here I've got A, which means that it should have the A1 attached to it. Over here I should have B1 attached to this one, and over here I should have C1 that's going to be attached to this one because that's just the way that the CSA default itself is going to be. Well, if I've got A1 attached to A, then I'm going to go and move across from A over to B. At my B point, I'm going to go across from my B1 down to C, and then at my C, I'm going to go across to my C1 down over to A once again. With all of these in place, now I can go and write out the other end. So this one over here is going to be my A2. Now we're going to no longer label these things as being A1, A2. We're going to start going with the actual high voltage designations right from the get-go. So the H1 of A goes to the H2 of A goes to the B. On my B's over here, I'm going to have the H1 of B, which is going to go to the B line, and I'm going to go and have the H2 of B, which is going to go to the C line. And then over here on my C's, I'm going to go and have the H1 of the C line, which is going to go to the C, and the H2 of the C line, which is going to go back to the A. And we see that we form a complete circle. The next thing that I want to do is I want to go and point out that I'm going to go and have low voltage windings that are going to go and be in parallel with these. I'm going to draw in little low voltage windings over here right now, just so we can move them over. And right now it seems really intuitive, but later on once we get delta y, this is going to turn into a really, really handy method of figuring out how you're going to do your secondaries. Over here we see we've got those low voltage windings that are the shorter lines I've drawn in there. What we're going to do now is we're just going to pick those up and we are going to go and carry them across, and we are going to go and form a delta or a triangle out of them. There's only one way that we can form a triangle out of them, and that's for me to go and connect them like so, across, etc. So I see that I would have these ones carried across like that. Now I want to go and bring this one back a second just so that we can go and take a look at where my ones are. The whole point of transform a polarity is that H1 has the exact same polarity as X1. In some cases, transformers don't even have a 1 listed. They're just going to go and have a dot that's going to be on there. But if I have got H1 over here on my main, that would mean that this would have to be my X1. Same as if I've got an H1 over here, my X1 would have had to have been the one that lined up with that one. Just erase those, and we will go... Oh no, I erased the wrong thing there. And we will go carry those ones back over. Okay, so I'm going to carry this one back over. Because we said that we're just matching these ones, H1 is on the right-hand side of the line, therefore my X1 is going to be on the right-hand side of the line over there. And my X2 will be over here. Same with my red. My H1 is on the lower left, therefore my X1 is going to be on the lower left, H2 on the upper right, X2 on the upper right. And then for this one over here, H1 upper right, X1 on the upper right, H2 lower right, X2 lower right. And then the very last thing that we're going to do is we're going to draw the lines in the same configuration. A line, B line, and then my C line over here. That takes care of my construction of my high and low side delta to delta transformer configuration. Note that this thing can be used as either a step down or a step up. I could be going from, let's just give these things some values. We're going to go and call this thing 600, and we're going to go and call this 240. I could be going from a 600 volt system. I could be using this thing to go and step it down to a 240 volt system. Or alternatively, I could be using it to go from a 240 volt system and step it up to a 600 volt system. Either one of these works, we just have to follow these lines. The next thing that we're going to do is we're going to go and take this that I've created over here, this is my paint by numbers map, and we are going to go and take it over to our actual transformer bank. Once again, if I was standing up top looking, those are my arms in front of me, if I was standing up top looking, I would want to go and have my A phase on the far right hand side. This means that when you walk up to a transformer bank, your A phase should be on the far right side. However, when I'm drawing them like this, I'm going to go and have my A phase in the left, just so that I can go and follow my other transformer convention, which is that I draw the high side on the top with the H1 in the left. High side on the top, H1 on the left. High side on the top, H1 on the left over here. Okay, with that convention in place, now we're going to go and draw lines across, and these lines are going to go and be representative of my high voltage buses, and they're going to be representative of my low voltage buses over here as well. Note that I'm not drawing out a neutral because we have no neutral for this thing to go and connect to, so it just kind of becomes redundant. The next thing that I'm going to do is I'm going to refer back to my drawing. This is my drawing over here. This is their drawing. It's identical. It's the exact same thing that we are going to go and have. But I refer back to my drawing and I see that on my high voltage side, all of my H1s go to the associated line. A, H1, B, H1, C, H1. So I'm going to go back to this drawing over here and I'm going to go and do the same. I see that I've got my A, my B, and my C like that. So I'm just going to pick my A, H1, goes up top over here. My B, H1, goes over here. And my C, H1, is going to go and tie to that one. Then I'm going to refer back to my handy-dandy chart, and I take a look at the far side of the same winding. My H2 of A goes to B. My H2 of B goes to C. My H2 of C goes to A. So we're going to go and carry that back to our other drawing here right now. This is going to, my H2 of A is going to go over to B. So I'm going to go and draw that as a black connection over there. My H2 of B is going to go over to C. I'm going to go and draw that as a blue connection over there. Oh, that doesn't make any sense. I drew that one connected to the black. Connected here to the blue. Well, I guess I did that with that one too. Sloppy work. Oh no, stuff is disappearing. All right, we'll just fix that up there. This H1 was supposed to go up there. Now we've got 2 connected to it. And last of all, on C, going back to this one over here, I see that for my C winding, the H2 connects back up to A. So I'm going to go and do that. My H2 goes back up to A over here. That is my high side designation. What you should note is that both of these, or all of these over here, if I take a look at any of my lines, I never have more than 2 connections. 1, 2 connections. 1, 2 connections. 1, 2 connections. If I've got a delta type of connection and I've got a line that only has a single connection to it, or I've got a line that's got 3 connections to it or something has been screwed up. There should always only ever be a single one. Okay, we're going to take a look at our low voltage side. The low voltage side, now once again, our A phase, the X1 goes to A. Our B phase, the X1 goes to B. Our C phase, the X1 goes to C. So we can go back onto these lines over here and we can do the same connections. I'm going to go and identify where my X1 is. These are all additive transformers. They're crossing over. So I'm going to go from my X1 down here. Then I'm going to go on my next one, my X1 down here, and then for my next one, my X1 down over here. Then I'm going to go back in, take another look at my drawing over here, and I see that on my A phase transformer, my X2 goes to B. On my B phase, my X2 goes to C. On my C phase, my X2 goes back to A. So we're going to go just following the alphabet over here onto my next lines over here. So X2 of my A phase goes down to B. X2 of my B phase goes down to C. X2 of my C phase goes back up to A. Once again, we are going to be checking and seeing if we've got 2 connections per line. 2 for that line, 2 for this line, and 2 for this line that we are going to go and have over here. So that is all checking out. I can go back over here, double check my connections, and I do have the exact same connections from there as what I have to this one over here. The next couple of diagrams inside of your book, 19 and 20 and 21, that's going to be this one here, 19, 20, and 20, 19 and 20 and 21, are all going to go and just show the same connection that I did. You can compare the connections that we have over here in full living color to the ones over here that are just black and white snips out of the book that we have over there. The other thing is polarity on our transformers is not going to go and be a big deal, whether we've got additive polarity or subtractive polarity transformers. We just have to go and make sure we copy our lines down correctly. Once again, the top side over here is done the exact same way. H1A, H1B, H1C, and then my A goes over to my B goes over to my C goes back onto my A. So this is identical to what we had before, but now on the low voltage side, we just see that we have now got subtractive transformers. They're not crossing over the core of the transformer, therefore these are subtractives. If I look at them, I'm going to go and note that we're still doing the same connections. X1 of the A goes to the A line. X1 of the B goes to the B line. X1 of the C goes over to the C line of these. And then my X2 of the A goes to the B. My X2 of the B goes to the C. And my X2 of the C goes back to the A. This connection, even though it is done with subtractive transformers, is identical to what we had drawn right over here on my X side. Make sure that you realize this, that just because we're going additive or subtractive, it doesn't matter what it looks like as long as the right X's and the right H's are going to the correct lines that we are going to go and have for these. And just like we had with the Y, we can actually go and mix our banks as well. Mixed banks are completely fine when it comes to my delta transformation. Over here, I see that I have got subtractive banks as well as I have got a additive bank that is going to be used. Once again, just look at these low voltage connections. The primaries are all, the high voltage sides are all correct. X1 of A goes to A, X1 of B phase goes to B, X1 of C phase goes to C, and then the rest of our connections are X2 of A goes to B, X2 of B goes to C, X2 of C goes back to A. Once again, the electricity doesn't really care. All that additive and subtractive means is that we have gone and had a specific winding to that. That it's going to go and be either wound around, both of them going in clockwise or both in counterclockwise or opposite to each other. It's all transformer construction based upon the company that put them together. We can take them, the individual ones, we can put them together in a bank. We just have to be careful with our connections like they're showing inside of this picture over here. The last thing that we're going to talk about is going to be my closure tests and my potential for faults on a delta bank. One of the very last things that I'm going to go and do on a delta bank is that I'm going to go and do what's called a closure test. That's going to go and tell me whether I have screwed things up badly or whether I'm safe to go and fully energize it. And it's going to be my delta transformer bank will be completed except for the very last connection that I have on there. So over here, if I take a look, I've got additive transformers over here that are going across. And if I take a look at my X1 of A goes over here, my X1 of B goes to my B line, and my X1 of C, we're just stopping that one for the time being over here. We're going to come back to that in a minute, but it should go all the way down to C. And then I'm going to go and do the opposite side. My A transformer, the X2 goes down to B. My B transformer, the X2 goes down to C. And my C transformer, the X2 goes up to A. This is a correct connections as far as we're concerned. If I take a look at my lines, I see no more than 2 connections per line. But the very last thing that I'm going to do is I am going to go and close in with a closure test. The closure test is theoretically supposed to be at a value of 0 volts. And what it would be doing is, right now, if I close in off of this, I should be coming from my A phase, if I were to look at it, my A phase to my B phase, back to my C phase. So I should have completed this loop and gone all the way back to a point where I'm at the exact same potential. In other words, there should be 0 volts. In practicality, there's always going to be a little bit of stray inductance, capacitance, magnetization, etc. And so I'm going to get a small value of voltage that is going to go and show up. And I'm doing this on my secondary side, by the way, not on my low voltage side or on my high voltage side exclusively. I'm doing it on the side that I'm supplying power. In other words, this is the side, in this case, there was high voltage bus existing and I was creating a low voltage system. But if I were to be creating a high voltage system using a step up, I would have done the closure test on the high voltage side over here. So I'm going to read a value of voltage that should be 0, but in practicality, it's going to be something anywhere from 0 going all the way up to line voltage. E line, anywhere in that range is going to be fine. If, however, I have screwed the connection up, I'm going to be reading double line voltage. And the reason for that is, really, if we take a look, what we just stepped through over there was we showed those transformer coils. We started with the A, the B, the C, and that technically there should be 0 because it's coming back to the same point as far as our phasors are concerned. But if I had one of my windings flipped, in this case, I have got the C winding that is flipped over here. What would actually happen is that I would have this thing extended out this far. And so if I take a look at these values, really what's happening is I'm measuring from this point to this point, which if this is E line and if this is E line, that means that I'm going to be measuring double my line value of voltage. So doing that closure test, you're always going to be looking for line voltage or less. It is going to be quite apparent, although the voltage value is going to be in between 0 and line voltage. As soon as we would go and have a fault, it is for sure going to be evident because it's going to go and become double line voltage. And if it's double line voltage, that is going to go and be danger. The other thing that we can do that is going to be bad but not horrible is we could go and connect our transformer bank accidentally for a 180-degree phase shift. Same as what we had inside of our Y to Y connection. If we look at it, the high voltage side is correct. The A on the H1, the H1 of the B goes to the B, the H1 of the C is going to the C, and then I've got the H2 of the A to the B, the H2 of the B to the C, and the H2 of the C back onto the A. Those are the standard connections that we have. But then what has happened is that our X1 and our X2 on the bottom side got flipped around. Basically, this drawing that we had over here, this drawing that we had over here, when it got put together, somebody just moved their X1s to their X2s and vice versa, but for all three of these. It is going to go and create another triangle. Watch this. I can go and take this X1 over here. I can create a different triangle. Blip. 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 Like that, going across. And when I do so, it's still a delta triangle, but what's happened now is that I've got my X1s moved over here, my X2s, etc. We just basically screwed up our whole connection because we didn't try to play the whole matchy-matchy game. These two sides should be equal. If they don't look the same, there's going to be some sort of an issue, okay? So let's just ignore all this dumbness that I just did over here because that's not what we want to do. Let's go back and take a look at how that would lay out in real life. In real life, we know that A line should be connected to my X1. But in this case, we see that my A line is connected to my X2. And that my B line, the X2, is connected to there, and the C line, the X2, is connected to there, which means that the rest of the connection, although it forms a delta connection and will go and spin three-phase loads, it is going to go and give us a massive, massive problem if we try to parallel onto a bank. Once again, you could do this as a standalone system, but it's not the standard, and it can hurt somebody else if they would go and put anything else on. Because generally speaking, this is what you're going to go and have ending up. You can see it's a delta, but what you would normally have is that you would go and have your A over here. You would go and have your B. Oh, that's black. B over here, and your C over here. And if I take a look at that, I now see that on a standard system, here's where my line A is, and that now I'm going all the way across from there to there if I were trying to parallel these together. This is going to be a catastrophic dead short. It is going to be roughly close to double your line-to-line value, and it's just going to go and destroy the transformers, switchgear, fuses, everything all at once. We just want to avoid that, and it's easy to avoid that. All we need to do is we need to make sure we do the correct connections. We don't do this over here. It's a triangle. Does this triangle match? No, this triangle does not match because it's an upsy-downsy triangle. We want all of our drawings of triangles to be like this, where it's going to go and be matchy-matchy, and this is a very, very good thing for us. All right, that is it for our deltas. We're now going to move on to some more complicated matters because we are now going to be combining both delta and Y out of the same transformer.